Welcome to a lesson on transformations of the cube root function. Here's the graph of the basic cube root function, which hopefully we do recognize, but if we didn't, we can always make a table of values seen here on the right. And we can actually use these 5 key points and this table of values to graph transformations of the basic cube root function. Let's take a look at our first example. Again, f of x equals the cube root of x. We want to graph y equals f of x plus 2, which would be the same as y equals the cube root of x plus 2. Notice what we're doing here is we're adding 2 to the function values, or the y values, of the basic cube root function, which means if we use these 5 key points from the basic cube root function, if we add 2 to each y coordinate, we can use those new points to graph this transformation. So let's go ahead and add 2 to each y coordinate. And now plot these new 5 points. So here we would have negative 8 comma 0 here, negative 1 comma 1, 0 comma 2, 1 comma 3, and 8 comma 4. So the graph of our transformed function would pass through these 5 points and look something like this. If we compare this graph to the graph of the basic function, notice how the plus 2 on the end here shifted the basic function up 2 units. So if we had minus a constant on the end, it would shift the graph down. Now we want to graph y equals f of the quantity x minus 2, which is equivalent to y equals the cube root of the quantity x minus 2. Notice in this case we're subtracting a constant from x, which would affect the input into the basic function f. So if we wanted to have the same y values as the basic cube root function, notice how here, because we're subtracting 2 from x, we'd actually have to add 2 to each x value to get the same output as the basic function, or the basic cube root function. For example, notice that when x is 0, for the basic function the output is 0. But for our function we'd have to use an x value of 2 to get the cube root of 0. So to find the 5 key points on this function, we can add 2 to each x coordinate and keep the outputs the same. It may seem like we should be subtracting 2, but because of the minus 2, we actually have to use larger x values to get the same outputs as the basic function. Let's go ahead and plot these 6 points. So we have negative 6 comma negative 2, 1 comma negative 1, 2 comma 0, 3 comma 1, and 10 comma 2, which would be off the screen, but it'd be somewhere in here. So our graph would look something like this. Because we added 2 to every x coordinate, this graph is the graph of the basic cube root function shifted right 2 units. If we have the cube root of the quantity x plus 2, it would shift the graph left. Now we have y equals 2 times f of x, which would be y equals 2 times the cube root of x. Notice how now we're multiplying the function values of the basic function by 2, which would be the same as multiplying the y coordinates by 2. So if we take the coordinates of the basic function and multiply the y coordinates by 2, we can find 5 points on our new function. Let's go ahead and plot these points. This first point would be negative 8 comma negative 4. Then we'd have negative 1 comma negative 2, 0, 0, 1 comma 2, and 8 comma 4. By multiplying the y coordinates by 2, we vertically stretched the basic cube root function by 2. Now we have y equals negative f of x, which would be equivalent to y equals negative, or the opposite of, the cube root of x. So notice our function here would change the sign of the function values, or the y values, of the basic cube root function, which means to graph this function, we can change the sign of the y coordinates of the basic function using our table of values. So this y coordinate would become positive 2. This would be positive 1, 0, negative 1, and negative 2. Let's go ahead and plot these 5 points. So negative 8, positive 2, negative 1, comma 1, 0, 0, 1, negative 1, and 8, negative 2, which is here. So here's the graph of our transformed function. Because we changed the sign of the y coordinates, it had the effect of reflecting the basic cube root function across the x-axis. Notice here where the y coordinates were positive, they're now negative, and where they were negative, they're now positive. Let's take a look at one more. Here we have y equals f of the quantity x plus 1 minus 3, which would be equivalent to y equals the cube root of the quantity x plus 1 minus 3. Looking at the plus 1 first, notice how this function is adding 1 to the x value, and therefore we'd have to subtract 1 from the x values of the basic function. So we'd subtract 1 here, 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 and here. We'd have to use smaller values of x because here we're adding 1 to x to get the value under the cube root. And this minus 3 on the end here would decrease the y value by 3, so now we'll subtract 3 from each y coordinate. Before we plot these 5 points though, we should begin to recognize that the plus 1 under the cube root, or f of the quantity x plus 1, would shift the graph left 1 unit, and the minus 3 on the end would shift the graph down 3 units. Here we have the point negative 9, negative 5, which would be here. And we have negative 2, comma, negative 4. And then we have negative 1, comma, negative 3. And then we have 0, comma, negative 2. And then we have 7, comma, negative 1. Here's a graph of our function. Comparing this to the basic cube root function, notice how it has been shifted left 1 unit and down 3 units. Now I'll leave you with some notes that will summarize the basic transformations. Here we have reflections across the x and y axis. Here we have vertical shifts, meaning shifted up or down. Here we have horizontal shifts, meaning shifts left or right. Here we have vertical stretches or vertical compressions. And here we have horizontal stretches and horizontal compressions. I hope you found this helpful.